in a way of an extra example that will illustrate the way that we proceed next, let us find the sum of the very first power series that we encounter in this course. To find the sum k from 0 to infinity, x to the power k, when absolute value of x is less than 1. So here x is a number that has absolute value less than 1. Our series here looks like so. It starts off with 1 plus x squared plus x cubed, and so on. You can see that ratio of every pair of consecutive terms is always x. So x to 1 is x squared to x is x, and so on. So the common ratio r is equal to x in this case. The first term is equal to 1. We can conclude that the sum of this series is equal to 1 divided by 1 minus x, because that's a divided by 1 minus r. Now, something fascinating happened here. So we have an equality which we know is true when absolute value of x is less than 1. And what this equality tells us is that this infinite sum of terms, each of which is a polynomial in x, is equal to this function. Right? So we just represented a function as an infinite sum of polynomials. So this is an example of something that we will call a power series, meaning it's a series that consists of powers of x, and this representation is the expansion of the function 1 over 1 minus x into a power series. As you can see, this expansion holds when absolute value of x is less than 1 and only for such x's. And so this is the very first power series expansion that we encounter in this course, and we'll study it in much more detail later when we start talking about power series. For now, I just want you to appreciate the fact that not only we can represent numbers as sums of infinite series of terms, each of which is a number itself, but also we can do the same thing with functions. We can represent functions as infinite sums of polynomials. And as we will see later, in this way we can represent much more complicated functions, such as the trigonometric functions, for example, as infinite sum of polynomials. And this is remarkably useful because it is not clear from this specific example, but computing sine x by definition is extremely tricky. So if you recall the definition, it's the projection onto the vertical axis of the point on the unit circle which corresponds to the angle given by the argument x, and so on. So computing sine of x by definition is a tricky procedure. Now instead, if we were able to reduce computation of sine x for any angle x to computation of a polynomial in x, we'd be much better off, because computing polynomials is just a matter of multiplying numbers together and adding them together. So that can be done relatively easily, either by human or by machine. Still, it's much simpler than abstract considerations such as find the point on the unit circle and then project it onto the y-axis and so on. So the motivation that we will have for considering power series later comes precisely from the realization that you can represent a large number of functions, even quite complicated ones, as power series in some intervals for x. So we'll talk more about how this interval for x is generally defined. More coming later, but for now, we'll just stop after obtaining our first power series expansion of a function.